Welcome to our NPTEL lectures on DC microgrid. Today we are going to discuss about DC microgrid versus conventional power systems and its similarity and the differences. So, our content today will be the central grid, which is a traditional grid which we are seeing for long 100 years. Structures of the conventional central power grid, then distributed generation and centralized power grid, structures of microgrid, interconnections of microgrid, management and operational issues of microgrid, then dynamic interactions with the main grid. So, that these are the topic we are going to cover in our discussions. So, central power grid. Central power, the central conventional power generation, that is, we shall take it as an abbreviation we will use in future, that is CCPG, is an electric power production by central station power plant that provide bulk of the power, and generally since it is provide bulk of the power, it required to be placed away from the load center, because that much of the land is not available in the load center. Most of them uses large fossil fired gas or the coal boiler, nuclear boiler to produce steam that drives the turbine generator. In some cases, large hydro may be used depending on the availability of the large dam and other facilities. These plants require costly management of large infrastructures, because it has a lot of power plant instrumentations and lot of land, you require lot of water and it is cooling. So, huge infrastructures and are susceptible to unreliability and instability under many foreseeable events. For example, huge landslide may break the dam, or you may have an earthquake or the enemy attack, all those things, or even in a cyber attack and you put actually all the turbine out of its synchronism. So, for this reason this has got a vulnerability in unforeseeable circumstances. So, structure of the conventional central power grid can be described below as: the conventional power grid is an interconnected network for delivering electricity from supply to the consumers, consisting of generating stations that produce electrical power, high voltage transmission lines that carry power from distant sources to the demand centers, and has distribution line that connect individual customers. So, you have a central generation, then we have a transmission network. Generally, if you want to send a power 1 kilometer away, you are supposed to step up 1 kV. So, you are sending a power in 100 kilometer away, you are supposed to step it up to 110 kV. Then transformer center. So, you have the transformer, then it will be stepping down, then generally it will be located in a switch gear that is outside the city. So, you do not want to bring a very high voltage inside the city. So, thereafter it will be taken underground and we have a small distribution transformer and the feeders feeding the load on the consumers. So, distributed generations and centralized generation, let us put it in a perspective. The value is we require continuous power, continuous quality power, mind it. So, distributed generation operated allow the facility to generate some or all of its power to a relatively continuous basis. Important distribution generation characteristics for continuous power include high efficiency and low emissions. And whereas in centralized operated to provide continuous power, its characteristics results in low efficiency due to high transmission losses at the transmission system and high emission. Corona, all those effects comes into the picture for the high voltage applications. Premium power, it provides power service at higher level of reliability and power quality than the typically available from the grid, that the power electronics required to ensure. Because you will choose a power solar inverter that actually generate power with THT less than 3%, whereas you may accept the THT in the grid may be 5% because of the industrial pollution. Provisions of a power at low reliability and power quality cannot be regulated due to the inherent high power losses, and also it is a feeding a consumers bulk consumer, and that is a polluting. Of course, we nowadays we are demanding high reliability, ultimately we require to have a power quality devices to correct it. Now costs. In a distributed generation, low variable costs, because you are generating from the solar, wind, and its cost is coming down, and also it has a low maintenance cost. Centralized generation, high variable costs because of the fluctuating nature of different prices. You know, since you are using a oil, let us say a gas fired based service station. So, then oil prices or the gas fires prices varies, your raw material prices varies, and thus you have a high variable costs, and also high maintenance costs, since you require to maintain the power from the generation to the end users. So, you have a different kind of people and different stakeholder all has to develop to give power. So, resiliency, we may have more of redundancy in case of the distributed generator. So, thus this gives to the resiliency, more resiliency since it serves low power demand continuously, less resilient because serves the high power demand continuously. Sustainability, sources of power makes it more sustainable, sources of power results less sustainability, because these are the issues, because it is uses the fossil fuel and most of this operation are not environmental friendly. Now, let us come to the structures of the microgrid. So, you have communication control, this is the blue dotted line, and red and green line are the electric network, and LC will be a local control. Now, and MC will have a micro generation control, and MGCC, that is microgrid system central control. So, you have a different hierarchical control to smooth operations of this microgrid. So, the basis structure of the microgrid system is presented in this figure, figure 2. Typically is consist of 2 micro generations or more than that, energy storage, micro source control, mostly it will control the quality of power it is feeding to the system, local control microgrid, central control, and electrical loads. Micro sources have plug and play features. So, if you wish in a day you are not here and do not want that solar power to be trapped, you may not trap, or you are having a maintenance issue, you can put your solar inverter off. There are so these are plug and play kind of devices. They are provided with the PEs, that is basically power electronics, to implement the control, metering, protection function during the standalone and the grid connected mode of operation. You may connect this point to the grid to exchange of the power. Once you have a surplus to the microgrid, you can sell it to the grid, or if you have a more load demand, you can take it from the grid, or you may operate in islanding mode. So, that also comes under the MGCC operation. So, microsource controller, operation and management of the microgrid in different modes of controllers coordinated through local microsource controller and the central controller. We may have a distributed controller and may have a centralized control. The main function of the microsource is independent control of power flow and the load end profile, the micro generation in response to the any disturbance and the load change. So, actually you have a source input disturbance, all of a sudden your irradiation level fall because of the clouding, then it has to see that what is the load demand, and it may cut down unnecessary load, or the reverse, you may actually get the greater sunny day all of a sudden, then your solar generation picks up, and then which they put into the queue some of the activity that may start. So, these are the tasks of this MC, where independently implies without communications with the center communication. So, this is something can do, and it is a distributed control in a local level. MC also participates in economic generation scheduling, load tracking or management, and demand side management by controlling the storage devices. It may also ensure that each microsource rapidly picks up its generation to supply its share load in standalone mode and automatically comes back to the grid connected mode with the help of central control. The most significant aspect of MC is its quickness, its in responding to the locally monitored voltages and current irrespective of the data from the neighboring MCs. So, this is the most important feature, that is point number this point. The control features enables microsources to act as a plug and play devices and facilitate the addition of the new microsources at any point of time to the microgrid without affecting the control and protection of the existing unit. So, if you want to have your existing solar power plant, you add another solar power plant, you are welcome to do that without having any hindrance to the rest of the microgrid. Then what is the task of the centralized control? Centralized control execute overall control of the microgrid operation and protection through MC. So, it get data from the MCs and ultimately it takes a supervisory role. What does it do? It maintains specific voltage and frequency in case of the AC microgrid, and in case of the DC microgrid only the voltage at the load end through the power frequency and the voltage control, and to ensure energy optimization for the microgrid. The CC, the centralized control, also perform protection, coordinations and provide the power dispatch and voltage set point for all the MCs. CC is designated to operate automatic mode with provision for the manual intervention whenever necessary. So, these are all intelligent control, but human being are given a right of option. So, sometime we have to set the priority of first for some conditionality. So, the authenticated person, administrator or someone have a right, super user has a right to write off. Interconnection of the microgrids. Microgrids are designed to generate power at distribution voltage level along with utilizations of waste heat. They have restricted energy handling capability. For this reason, the maximum capacity normally restricted approximately is 10 MVA as per the IEEE recommendation. So, that is also quite big power from the Indian perspectives. In microgrid, it is possible to supply large amount of load from several microgrid through a common distribution network by splitting the load pocket into the several controllable local loads. That is also localization, is called localization of the load. In this way, microgrid can be connected from much larger power pools for meeting bulk power demand. For interconnected microgrid, each centralized control must execute its control in close coordination with the neighboring microgrids. Thus, an interconnected microgrid would achieve greater stability and controllability with the distributed control structure. Now, interconnection of the microgrid to the main grid have the following importance. That is what we have seen, that there is a point of injection, that is called point of common coupling. That is availability of the grid. Definitely, you may put a microgrid in isolated places, there is no grid, then there is no question of grid connectivity arises. So, availability, highly available power grid may act as a additional source for the microgrid. Direct connections of AC microgrid to a large power grid facilitates stable operation, but only if the power grid acts as a steep source to the microgrid. When using a renewable energy sources, a grid connection may allow reducing the need for the energy storage in the microgrid. For this reason, actually it is quite helpful, because there is a concept of autonomy. Let us say you have a mostly solar microgrid, and ultimately you may consider that there is a rainy day and thus generation of the power will be low, and for this reason we require to design the battery size. So, if you have that grid connectivity, then you may consider that okay, battery size can be lower. So, you may not, because power may go up not throughout the day. So, for this reason one day power backup may be sufficient, but if it is islanding more, then what will happen? The cost of the battery will increase. If not all the loads in a microgrid are critical, so that is very important thing. So, and that is also true most of the cases, you have around 20% or 10% of the loads are the critical load. So, grid connection may allow to reduce the investment in a local generation. So, once let us say you are using a high bulk power consumption, when actually power availability to the microgrid is scanty, you can schedule your work at that time. So, interconnection of the microgrid with utility grid. One reason is the economics. Microgrids are typically planned. So, for this you can see that these are wind generations, this is a PV module, this is the micro turbine, and you may have a fuel cell, and ultimately power electronics comes into the pictures, and this is the battery, and this is a microgrid distributions, or you may have and this is the controller. Through that it is active power rectifier generally or filtered depending on the bidirectional power flow happens from the grid to the microgrid and vice versa, and you may have a bulk of the energy storage to exchange the power, and power electronics load interface can be done by it. So, this is a interconnected microgrid system. Microgrids are typically planned with the extra capacity with respect to the local load. This extra power capacity can be injected back to the grid in order to obtain some kind of economic benefit. Generally, we have a tariff benefit once you sell the power to the grid instead of taking. That is the way of we incentivize to set up the microgrid. Grid connection allow to reduce fuel operation cost by using a grid at night when electricity costs are low. Point of common coupling is the point where microgrid connected at the main grid. So, this is the overall operation we are going to explain into the next slide. Interconnection method, definitely it can be directly to the switch gear. This is a traditional method. Power electronics interfaces. So, now we have a solar inverter and islanding techniques, all those been placed, and they have a static switches mostly for the maintenance purposes, and directly through the circuit breakers also you can do that. Relatively simple and inexpensive, but it require cycles of operation slow 2 to 3 cycle to achieve the complete disconnections. Since electrical characteristics on both the side of the circuit breaker must be the same, then electrical characteristics on the microgrid side are dependent on the grid side characteristics. Let us put an example, then only you understand better. For example, use circuit breaker implicitly limit the microgrid to have at least partially as an power distribution system in order to match that grid characteristics. Otherwise, there is that impedance matching is a very big issue. So, those aspect has to be put into the aspects, and power flow through the PCC cannot be controlled if you have this option, that is with the static switches or the direct through the switch gear. So, power flow will be totally depending on the load. So, interaction with interconnections also we can place some kind of checks and balance by the technologies. So, of course, if you use the static switches, then you see that what happened. It is usually based on the SCS and in anti-parallel configuration to allow the bidirectional power flow. Depending on the rating, if your rating nowadays we are coming with the high bandgap devices SIC. So, these SCS can be soon replaced by IGBTs. They are costlier and the more complex than the circuit breaker, but advantage is that power flow can be controlled. Usually conventional circuit breaker are still used to provide the way to achieve full galvanic isolation. A bypass switch also added to maintain for the maintenance region. I was saying that for maintenance purpose we require to have a isolators. They allow many close or open operation. They act much faster than the conventional circuit breaker in order to the half of the circle. Sometimes IGBTs are used instead of SCS, that is what I am saying, and IGBT will find its more space with while this high bandgap devices are put into the practices. IGBTs tend to be the faster than SCS and their current inherently limited. Still power flow cannot be controlled, there are some conduction losses in the devices. For this reason we are also researching in that area, and we are talking about SiC based devices to take care of the low power flow losses. Now comes into the third entity, that is power electronics interfaces, interconnection by the power electronics devices. it is the costlier option till now. Of course, we expect that cost will come down gradually. It is the most costlier option, however, it is most flexible one. It allow power distribution architecture characteristics to both sides of this PCC to be completely different. You can have a different frequency here, you can have a different frequency, you can have a different voltage level, everything can be different. Both real and the reactive power flow can be controlled, that is the PQ control, and generally the power entry is through the active power filter or rectifier. Reaction times of the connection and disconnection command are similar to those of the provided by the static switch, because it also uses IGBTs only. Although this cases the power electronics, its response depends on the dynamic performance given its controller topology and the internal energy storage component and characteristics. Still, in many cases the circuit breaker will still be required at the grid site, because you have to have a arc quenching and all those leakage current, those issues has to be tackled. Terminal electronics interface with the local area and energy system in order to provide a way of the physical detection of the microgrid from the grid, and also leakage current was a very big issue. Presence of the power electronic circuit also will lead to some power losses not found in the approach of the mechanical interference, because till now we do not find a seamless transition of power electronics turn on to turn off, because there is a turn on turn off losses as well as the conduction losses in case of the power electronics devices. So, next, the last important thing is the management and the operation of the microgrid. Major management and the operational issues related to the microgrid are this: power quality, active and the reactive power balance must be maintained within a microgrid on the short term basis. So, it has to be balanced in a particular time frame. Microgrid should operate standalone in a region where utility supply is not available, or the grid connected mode within a large utility distribution network. The microgrid operation should be able to choose the mode of operation within proper regulatory framework. Generation, supply and the storage of the energy must be suitably planned with respect to the load demand and the microgrid long term energy balance. Supervisory control and the data acquisition based metering, control and the protection function should be incorporated in the microgrid controls and the MCs. Then microgrid operation should be ensured through generations, scheduling, economic load dispatch and optimal power flow operation. These are the different considerations we have to keep in mind. System security must be maintained through the contingency analysis and emergency operation like demand side management, load shedding, islanding and the shutdown. This can be practiced whenever it is required seamlessly. Under contingency condition, economic scheduling of generation should be done to take care of the system loading and the load and voltage frequency regulations. Temporary mismatch between generation and the load may be alleviated to the proper load forecasting and demand side management. The shifting of the load might help to flatten the demand curve and hence reduce the storage capacity. So, for this reason and the dynamic interactions with the interaction of the microgrid with the main grid. This is one of the important aspect of it, please put attention to it. Since capacity of the microgrid being sufficiently small, since we are saying the word micro, the sustainability of the main grid is not affected when connected to the main grid. Please understand that. It is always actually the smaller entity will be affected. However, in future the microgrid will become more commonplace with higher penetration of the DES, distributed generations, and the storage element. The stability and the security of the main grid will be influenced significantly with the presence of the microgrid. The dynamic interaction between the microgrid and the main grid will be a key issue in operation and the management of both the grid. That is the challenge we are going to face in future. The dynamic interaction between microgrid and the main grid will be a key issue of operation and the management of the both the grids. Microgrids need to be designed properly to take care of their dynamic impacts on the main grid such that local stability, reliability of the whole system is significantly improved. So, these are few issues of the dynamic operations and the dynamic interactions on the microgrid with the main grid. And then this is the smart communication network utility grid, and this is the microgrid, and you have a supervision, you have a dynamic pricing, you have a peak load shaving, thereafter grid power supply prediction, all those, and ultimately microgrid interface is the local energy management, cost optimization, weather forecasting, power demand forecasting, smart metering, monitored and end users. These are all come into the one package when it is the interactions with the main grid matters. So, the microgrid controller provide the interface between the utility grid and the load, aiming at an optimal power flow management. So, this is the figure that describes that. So, figure shows that power management interface principle based on the main data which have exchange between the microgrid and the utility grid. And what else? The microgrid controller can take into the account of the information about the public grid availability and the dynamic pricing, inform the smart grid on injection of intentions of the power demand, meet the demand of the end users with respect to all physical and the technical constraint, operate with the best energy cost for the public grid for the end user, and thereafter it can to satisfy this objective as well as the forecasting, smart metering, monitoring and the actions prescribed in the figure. A specific interface associated with the microgrid are to be designed and to be implemented. Thank you for your attention. These are the few things while we will connect the microgrid with your main grid.